Hi everyone, I would like to share some results about our ongoing work on establishing a reflection for effect handlers. The motivation of this work comes from the question of how to prove correctness of compilers for effectful languages. Among different ways of proving compiler correctness, there is an approach that uses the relationship between the compiling and decompiling functions. In this approach, we show that the composition of compiling, evaluating in the target, and decompiling is equivalent to evaluating in the source. When the two horizontal arrows in this diagram imply each other, we call the relation a Galois connection. And when we have an additional equality stating that decompiling and then compiling is syntactic identity, we call the relation a reflection. So far, reflections have been developed in three settings. The earliest work considers a pure call-by-value source language, and later work extends the results with delimited control operators. These reflections all require a fine-tuned compiling function, which gives us a rigorous correspondence between source and target reductions. They also require a carefully designed target calculus, which precisely characterizes the image of the compiling function. Building on these studies, we aim to develop a reflection for algebraic effects and handlers. Our approach is to follow the recipe of the existing reflection for the shift 0 and dollar operators, which are known to be equally expressive as deep effect handlers. The result so far is that this approach allows us to prove most but not all properties required of a reflection. This is a bit surprising given the close relationship between effect handlers and control operators. Towards the end of this talk, I will explain why the proof fails and how we could possibly make it work. Okay, so here's our source calculus. The calculus is an extension of the untyped lambda calculus with operation calls and effect handlers. It is formalized as fine-grained call-by-value with a strict separation between values and computations. There is also the notion of pure evaluation contexts, which are built from let frames. The reduction rules are all standard. A handler transfers control to the return clause when its body is evaluated to a value. An operation call shifts control to the operation clause of the surrounding handler while capturing the delimited continuation within that handler. Other than this, we have beta and eta rules for application and let expressions, as well as an associativity rule for let expressions. So we are going to develop a reflection for this language by going through the 4 steps listed here. First, we define a compiling function, formalize its image, and prove that compiling preserves reduction. In the reflection literature, the reduction preservation property is called monotonicity. Second, we define a decompiling function, formalize its image, and prove monotonicity of decompiling. In the reflection terminology, the image of decompiling is called the kernel of the source calculus. After these steps, we prove 2 relationships between compiling and decompiling. One of them states that decompiling and compiling is syntactic identity. The other one says compiling and decompiling yields a reduced version of the original source term. The 2 properties are called right inverse and left pulse inverse, respectively. Okay, so let's start with step 1. Here we define a CPS translation as the compiling function. The translation is formalized as a column translation. This is a well-known technique for avoiding administrative reduxes, and it gives us a rigorous correspondence between source and target reductions. As we can see, Our column translation has two continuations. The first one is a pure continuation, representing the composition of let frames and the return clause of the surrounding handler. The second continuation is an effect continuation, representing the operation clause of the surrounding handler. By looking at individual clauses, we see that we use a special aspirant construct for the translation of operation calls. The construct is a syntactic sugar of this lambda term, which has duplicate occurrences of the effect continuation H. The duplication of H gives rise to non-standard restrictions on the syntax and reduction, and we avoid them by introducing the aspirant construct. To give you a better idea of how the translation works, let me show you an example. The source expression is a handler construct, and its CPS image is a function whose body is an aspirant term. The aspirant comes from the operation call, and among the three sub-expressions, the pure continuation here is a composition of the let frame and the return clause, whereas the effect continuation here represents the operation clause. Based on this CPS translation, we next formalize the target calculus. The calculus consists of 6 categories of expressions, and as we can see, some of them have an annotation delta. The annotations tell us what continuation variables are in scope, and they allow us to precisely characterize the image of the CPS translation. As a consequence of having annotated expressions, we have multiple variations for each reduction rule. For example, these are 3 variations of the beta rule for application, and as we can see, each variation takes care of a radix with a different annotation. With the CPS translation and target calculus defined, we prove the monotonicity property. The property states that if a computation M1 reduces to M2 in the source, then the translation of M1 reduces to the translation of M2 in the target. To prove this, we first show some lemmas about the column and value translations, and then derive the goal as a corollary. This completes step 1. Let's move on to step 2. In this step, we define a direct style translation as a decompiling function. Here is an excerpt of the translation. For root expressions, we remove the 2 continuation abstractions. For function application, we apply the value translation to the function and argument. In the next 3 cases, we generate a term embedded in some context. The context is either a let frame, which we reconstruct using the flat translation, or a handler, which we reconstruct using the double flat translation. Note that we need a substitution in the aspirant case. The substitution specifies the handler of the captured continuation, and it is part of the semantics carried by the aspirant construct. To better understand how it works, let us translate our CPS example back into direct style. The target expression is a root term whose body is an aspirant, and its DS image is a handler term whose action is an operation call. The return clause is reconstructed from the pure continuation, whereas the operation clause is reconstructed from the effect continuation. Based on this translation, we formalize the kernel calculus, which is a subset of the source calculus. The kernel calculus makes a distinction between terms and non-values, And this distinction leads to two invariants. First, let expressions cannot be nested, and second, handlers cannot surround a let expression. The reduction rules of the kernel calculus are designed so that they maintain the two invariants. Specifically, when we perform a beta reduction, we apply a post-processing of the resulting term via the colon and semicolon operators. These operators flatten nested let expressions and push let expressions into the return clause of the handler. Having defined the DS translation and the kernel calculus, we prove the monotonicity property. Again, we first show some lemmas about auxiliary functions and derive the main statement as a corollary. Okay, so far we have discussed the CPS and DS translations individually. Now we turn our attention to their relationships. One of the relationships we would like to have is that compiling is the right inverse of decompiling. The first proposition here is our main goal, and it is proved with several auxiliary propositions by mutual induction. Due to the fine-grained syntax of the target calculus, there are a lot of cases to go through, but we were able to prove this property. The other relationship we want to have is that compiling is the left path inverse of decompiling. Again, the first proposition is the main goal, which needs some auxiliary propositions, but it turns out that these propositions do not hold. What we failed to prove is one case of the third proposition, namely this one. We would like to show that the first line reduces to the fourth line. An important observation here is that the first line is not a well-formed term in the kernel calculus, as the handler surrounds a let expression. This means it cannot be syntactically equal to the result of DS translating a target term. So we need to somehow convert the first line to a legal kernel term. The conversion is possible if we add to the source calculus a reduction rule like this, which we call hlet. Roughly speaking, the rule defines the interaction between a let expression and a handler. More formally, the rule says, when we have a handler surrounding a let expression, we can push the let frame into the return clause of the handler. This is intuitively correct, but it is not sound with respect to our CPS translation. Indeed, if we CPS translate the redux and reduct, we obtain different results. The CPS of the redux tells us that the body M of the let expression is handled by some handler H prime that happens to surround it at runtime. On the other hand, the CPS of the reduct tells us that the body is handled by the same handler as the definition M. So the latter is more specific about the handling of N, and it is consistent with the deep handler semantics, which wraps the captured continuation around the original handler. The problem is that in the CPS translation, the deepness is enforced by operation calls, not handlers. If we look at the translation of operation calls here, we see that it passes the effect continuation H to the pure continuation K. And that is why the handler for N is unspecified in the CPS of the redux here. The CPS translation of handlers does not specify the handling of the continuation, so the handler of N is just a variable. From our failed proof, we can deduce that for a CPS translation to constitute a reflection, it must satisfy one of the two conditions here. The first one is the translation must separate let frames and the return clause instead of merging them into a single pure continuation. This would allow us to reconstruct let expressions in handlers through the direct style translation, and thus make the source and kernel calculi closer. The second condition is the translation must give handlers the responsibility for enforcing the deep handler semantics, not operation calls. This would allow us to accommodate the extra reduction rule, namely hlet, in the source calculus, and use that to connect the source and kernel calculi. That's the lesson we learned so far. As the next step, we plan to try a different CPS translation given by Hillerstrom et al. In their recent JFP paper. The translation is promising because it satisfies both conditions we derived. It also supports shallow effect handlers, which do not insert the original handler into a captured continuation. However, the translation is much more complicated than the one we have been using so far, and this may pose other challenges to the proofs. Before wrapping up, let's do a quick comparison between effect handlers and shift0 and $. As I mentioned in the beginning of this talk, these language features are closely connected to each other. More precisely, an operation call corresponds to shift0 and a handler corresponds to $. The difference is that while the interpretation of an operation call is given by a handler, the interpretation of shift0 is given by itself. This syntactic difference affects the usability of these constructs. Many people argue that having a separate handler makes it easier to write modular programs. However, from the viewpoint of reflections, the modular aspect of effect handlers seems to be the source of complication. As we have seen, we need to pass around an additional effect continuation in the CPS translation. The presence of effect continuations makes it hard to have the hlet rule in the source calculus. And the lack of this rule prevents us from proving the left pos inverse property. In the case of shift0 and $, there is no notion of effect continuations, so it is possible to have a source reduction rule that behaves like the hlet rule, and use that rule to prove the left pos inverse property. Alright, I have talked about our attempt to develop a reflection for effect handlers. Our take-home message is that to obtain a reflection, it is very important to pick a right compiling function. We are still halfway through, but we believe that the lessons learned so far will bring us one step closer to our eventual goal. We also think that these lessons can be applied to reflections for other language features. Thank you.